Welcome to Caltrans LSIT LS exam preparation course. One aid in your preparation for California licensure examinations. A word of caution, don't use this course as your only preparation. Devise and follow a regular schedule of study which begins months before the test. Work many problems in each area, not just those in this course's workbook, but problems from other sources as well. This course is funded by Caltrans, but you and I owe a profound thanks to others, the course's instructors, from the academic community, the private sector, other public agencies, and from Caltrans as well. We wish you well in your study toward becoming a member of California's professional land surveying community.
Welcome to today's discussion of the State Plane Coordinate System. A 1986 change to the Public Resources Code of the State of California created the California Coordinate System of 1983, noted as CCS 83. The implementation of the system is to be phased in by January 1st, 1995, when state plane work must refer to it in most cases. It replaces the previous system of 1927. The old North American datum of 1927, developed by the U.S. Coast and Geodetic Survey, was the basis for CCS 27. It used an approximation of the Earth's surface in North America named Clark's spheroid of 1866 as its geodetic reference surface. The North American datum of 1983, that's NAD 83, developed by the National Geodetic Survey, underlies CCS 83. A new ellipsoid, the Geodetic Reference System of 1980, also called GRS 80, is the basis of the new system. This ellipsoid is geocentric and approximates the surface of the entire Earth, not just North America. Because the geodetic reference surfaces are different, the NAD 27 latitude and longitude of a station differ from the NAD 83 values for the same station. Overlying those differences are the factors that the adjustment incorporated new observations. The adjustment used was a least squares simultaneous adjustment of the entire system, and that blunders could be isolated and culled. In fact, the variation between the two coordinate systems vary inconsistently, making only approximate transforms possible. At present, rigorous computation of coordinates is only possible by returning to the original field observations, readjusting and recomputing positions from them. The designers of the coordinate system limited the north-south extent of each Lambert grid to meet certain predetermined criteria. Therefore, 6 zones comprise CCS 83. Zone 1 is at the north end of the state. The zone numbers increased southerly until Zone 6 extends to the Mexican border. Each zone is based upon a cone whose axis is coincident with the GRS 80 spheroid axis of rotation. The cone is a secant cone because it intersects the surface of the ellipsoid at 2 standard parallels rather than simply resting on it. This minimizes distortion while projecting data from the ellipsoid onto the cone. As enacted by the state legislature, the new coordinate system's linear units can either be meters or U.S. survey feet. To date, NGS has implemented NAD 83 as a metric system. It has published all CCS 83 station data in meters. State plane coordinates expressed in one unit can be converted to the other unit simply by multiplying the northing and easting by the foot meter equivalency. This will be described later in this presentation. One may work the California coordinate system in either feet or in meters, but one must be consistent. Not only must all distances be uniformly in feet or in meters, but tabled constants must also correspond consistently with the linear unit used. This discussion is presented in terms of meters, but the accompanying written material is presented both in feet and in meters. The NGS recommends using polynomial coefficients in algebraic equations to simplify calculations for state plane coordinates. Polynomial coefficients are easy to use. Therefore, they are appropriate for both manual and programmed calculation applications. Through their use, projection tables become unnecessary. They can produce millimeter accuracy using handheld calculators carrying only 10 significant digits. The NGS developed the coefficients by polynomial curve fitting of an array of data points for each zone. For those wishing to use projection tables, the California Land Surveyors Association has published a book of projection tables as special publication number 55/88. NGS is now publishing a similar table. Please be aware, if you are preparing for the Land Surveyors examination, the new coordinate system will be phased in through the beginning of 1995. However, nothing prevents the State Board from asking questions about the older system on future examinations. You need to prepare for both. While this presentation concentrates on the California coordinate system of 1983, it is broadly applicable to the system of 1927. Calculations for the older system are not as sophisticated as those used now. Therefore, if you understand the system of 1983, it is much easier to master the older system. State plane coordinate systems are intended to permit the calculation of positions on a grid using measurements made on the curving surface of the Earth and at different elevations. If those measurements are accurately made and extended over a long distance, plane geometry calculations will yield inconsistent values for the position of the stations. The state plane coordinate systems were devised to provide a calculation technique that produces coordinate values that correctly relate to each other even over long distances and compare favorably with those calculated by geodetic means. First, we will look at a series of pictures to help us visualize the coordinate system. The first set of illustrations is intended to acquaint us with the relationship between the ellipsoid and the cone that is the basis of the system. We now see depicted the geodetic reference system of 1980, also referred to as the GRS 80 system ellipsoid. It approximates the shape of the planet Earth. Like the Earth, it is slightly flattened. The polar radius is about 13 miles less than the equatorial radius. The GRS 80 ellipsoid underlies the California coordinate system of 1983, or CCS 83. The National Geodetic Survey developed the recently revised coordinate system. The system uses information from the North American datum of 1983, NAD 83, adjusted during the period 1975 through 1986. We also see depicted the axis of rotation of the ellipsoid that is the same as our planet Earth's axis. We now see the addition of the equator. The equator is formed by the intersection of the surface of the ellipsoid with a plane that is at right angle to the axis of rotation and located midway between the poles of the ellipsoid. Next, two latitudes are presented north of the equator. These two latitudes are defining elements for each portion of the California coordinate system. Each selected latitude is called an exact scale or standard parallel. Latitude is measured by the angle formed at the intersection of the equatorial plane with a line normal to the surface of the ellipsoid. The two latitudes are called the north and south exact parallels. and noted as B sub n and B sub s. Now we see a cone generated through the two exact scale parallels. This means that it is a secant cone. In other words, the surface of the cone is within the surface of the ellipsoid between the standard parallels and outside it towards its apex and towards its skirt. The axis of the cone is coincident with the axis of rotation of the ellipsoid. For each unique pair of standard parallels, a unique cone will be created. Another parallel of latitude occurs between the two standard parallels where the separation between the ellipsoid surface and the cone is greatest. This latitude is nearly midway between the standard parallels, and therefore its name is the central parallel. Its notation is B sub O, representing the latitude of the origin of the projection. Each zone has its own central parallel, a tabled constant for that zone. For each zone, the geometry of the cone fixes the distance from the apex to the central parallel. The notation for that distance is R sub O, standing for the mapping radius of the projection origin. The angle between the axis of the cone and its surface will have a value that is equal to the latitude of the projection origin. Next, we see a geodetic meridian of longitude projected onto the cone. That is a true north-south line. The designer of the zone has selected a particular meridian to fulfill best the needs of those who will use the zone. It will form the center of the east-west extent of the zone. Therefore, it is called the central meridian and is a tabled constant. At the intersection of the central meridian with the central parallel is the projection origin. Now we see the addition of another parallel of latitude. It is the north geodetic latitude of the grid origin. At its intersection with the central meridian is the origin of the grid. In every zone, that point is assigned a northing value of 500,000 meters and an easting value of 2 million meters. The notation for the latitude of the grid origin is B sub B because through it will pass the baseline of the grid. Associated with the grid latitude of the grid origin is a particular distance from the apex of the cone. This distance is known as the mapping radius through the grid origin, noted as R sub B. It is a tabled constant for each zone. Next, we see the customary north-south limits of the grid and the customary east-west limits of the grid illustrated. These limits are customary only. When there is a good reason for doing so, the grid may be expanded beyond them. Before we continue to our next graphic, let's look at a simple model with a paper cone representing the large cone with its apex way above the north pole of the ellipsoid. On this cone, we can see that the geodetic meridians have been projected through, and they form now north-south geodetic lines. You'll also see that the latitude line has been projected through so that they form what appear to be parallels on the cone's surface. Now, the interesting thing that this cone is to illustrate is that when we develop this cone, that is, when we flatten it out, which we'll do right now, those lines that appeared to be parallel become large semicircles here. And the lines that used to be running to the apex of the zone now converge at a point. So the geodetic meridians converge while the parallels of latitude become large arcs of circles. We will now see a series of pictures portraying the developed cone, that is, the cone once it is opened up and flattened into a plane. On that developed cone, we will see the various lines that relate it and the grid that creates the state plane coordinate system. This picture shows the cone for a zone developed that is opened up and flattened. The cone entirely encircled the ellipsoid. In other words, it represents a full 360 degrees of longitude. But now that it has been developed, the central angle at the apex of the cone is considerably less than 360 degrees. The central angle at the apex of the developed cone equals 360 degrees times sine b sub o. This gives us the ratio that we can use to proportion differences in longitude when calculating the corresponding central angle on the developed cone. Sine b sub o is the sine of the latitude of the projection origin, a tabled constant. The latitudinal line illustrated for our developed cone is b sub o through the projection origin. We see that the mapping radius of b sub o has been labeled as r sub o. It is the distance from the line of latitude b sub o to the apex of the cone, a tabled constant. Now added is the northing axis. The northing axis coincides with the central meridian. Therefore, its longitude is the same as that of the central meridian, passing through the projection and grid origins. Next, we see the addition of another latitudinal line and its mapping radius. The latitude is that of the parallel passing through the grid origin. Its latitude is noted as b sub b. It is a tabled constant for each zone. The mapping radius is labeled as r sub b. It is the mapping radius through the grid origin and is a tabled constant. Next, we see the addition of the easting axis. It passes through the grid origin and is at a right angle to the central meridian. Next can be seen lines of longitude approximately delineating the customary east-west limits of the zone. Also added is a segment of the latitude approximately delineating the customary northerly limit of the zone. The customary southerly limit is the easting axis. Next, a meridian of longitude extends from the apex of the cone to a station which coincidentally is on the central parallel. A longitude is a true north-south geodetic line, a geodetic meridian. The notation for the west geodetic longitude of a station is capital L. If we create a grid north line through the station, it will be parallel with the northing axis. The plane convergence angle is the angle formed on the developed cone between the central meridian and the line of longitude through the station. Lowercase gamma symbolizes the plane convergence angle. It can be seen on the screen that the difference between grid north and geodetic north at the station equals the plane convergence angle at the apex of the developed cone. The plane convergence angle is equal to the difference between the longitude of the central meridian and the longitude through the station multiplied times sine b sub o. Both the longitude of the central meridian L sub o and sine of b sub o are tabled constants for each zone. This principle imposes the same proportioning previously imposed upon the central angle for the entire cone. Let's now look at another set of illustrations dealing with the grid. It will make clear the grid's construction and its relationship to certain elements of the cone and ellipsoid. On the screen, we see the two standard parallels of geodetic latitude. Each California coordinate system zone has two of these lines of exact scale where the cone intersects the surface of the GRS 80 ellipsoid. The northerly one is noted as B sub n and the southerly as B sub s. Now we see the circular arc of the central parallel added to the illustration. Noted as B sub o, it is a parallel of latitude that is approximately midway between the standard parallels. Along this line occurs the minimum scale within the zone. Associated with the central parallel is its mapping radius, the distance from the apex of the cone to the central parallel, a distance noted as r sub o. Both the latitude of the central parallel and its mapping radius are tabled constants. Next, we see the addition of the central meridian. It is the projection of a true north-south geodetic line noted as L sub o. The central meridian also is the northern axis of the grid. It passes through both the projection origin and the grid origin. As such, its notation is also E sub O. By definition, the central meridian has an easting value of 2 million meters in all zones. At the intersection of the central parallel and the central meridian is the origin of the projection. This location has geodetic coordinates, that is latitude and longitude, of B sub O by L sub O. We now see another parallel of latitude has been added. Noted as B sub B, it is the projection of the geodetic latitude passing through the grid origin and is a tabled constant. It also has a particular mapping radius associated with it, a tabled constant noted as R sub B. At the intersection of the central meridian with B sub B is the origin of the grid. Consequently, its geodetic coordinates are B sub B by L sub O. Through the grid origin and at a right angle to the central meridian runs the easting axis of the grid. It is the baseline of the grid noted as N sub B. A northern value of 500,000 meters is associated with the easting axis. Therefore, the origin of the grid has plane coordinates of 500,000 meters northing by 2 million meters easting. This is true for all zones by definition. Parallel with the baseline of the grid and passing through the projection origin is an east-west grid line. Its northern value is noted as N sub O, a tabled constant. Therefore, the grid coordinates of the projection origin are N sub O by E sub O. On the screen, we see the approximate customary east-west extent of the zone depicted. These limits are customary only, but it is usually not necessary to extend the coordinate zones too far into the Pacific Ocean or into adjacent states easterly of us. Next on the screen, we see the approximate north-south customary limits of the grid. The customary southerly limit is the baseline of the grid. More grid lines are added parallel with the northern axis. Each line runs grid north. Remember that geodetic meridians converge toward the apex of the cone, while grid meridians are not parallel, are all parallel. Therefore, the difference between geodetic north and grid north at any particular point on the grid depends upon the position of the point. Now, grid lines paralleling the easting axis have been added to the display. They all run grid east and at a right angle to the north-south grid lines. Now that we understand the basic geometry of the ellipsoid, cone, and grid, we will view a series of pictures illustrating the geometry that allows us to convert geodetic coordinates, in other words latitude and longitude, to state plane coordinates, our familiar northings and eastings. We now see on the screen a single line of latitude projected onto the developed cone's surface. This line of latitude is the central parallel of the zone, noted as B sub O. The central parallel is a tabled constant for each zone. We now see the central meridian, a geodetic north line, added to the picture on the screen. This line is also the northern axis of the grid. All other grid north lines will be parallel with it. Its easting value is 2 million meters by definition. That value is noted as E sub O and is a tabled constant. The intersection of the central meridian with the central parallel is the projection origin. Now we add the easting axis or baseline of the grid, noted as N sub B. This line runs at a right angle to the northern axis. Its northern value is a tabled constant and is 500,000 meters by definition. This northern value sometimes is called its false northing. The intersection of the northern axis with the easting axis is the origin of the grid. The screen now shows a dimension line extending from the apex of the cone to the grid origin. This distance is the mapping radius through the grid origin, noted as R sub B. It is a tabled constant. By inspection, we can see that by adding together N sub B and R sub B, we can calculate the northing of the apex. Now added to the display is a station at which the geodetic coordinates and the grid coordinates are to be equated. we see a parallel of latitude added through the station. Its latitude is noted as capital B. Next added is a geodetic meridian of longitude extending from the apex of the cone to the station. The notation for its longitude is capital L. Now another line has been added. It is a line through the station extended at a right angle from the northing axis. The latitude through the station has a particular mapping radius associated with it. Labeled as capital R, the length of the mapping radius through the station can be measured along the meridian from the apex to the station. As shown on the screen now, the central parallel has its own particular mapping radius noted as R sub O. It is a tabled constant. The value of the mapping radius R through our station will be needed for converting geodetic coordinates to state plane coordinates, and vice versa. So that we can do this, NGS devised a method to calculate the radial distance between the parallel of latitude through our station and the central parallel. It involves the use of equations employing tabled coefficients and the difference in latitude between the origin of the projection and the station. The distance obtained by this method is labeled small u on the screen. When a station is north of the central parallel, u is negative. When the station is south, it is positive. By inspection, it is apparent that the mapping radius of our station R equals the sum of the mapping radius through the central parallel, R sub O, and the radial difference, u. Remember that we previously discussed that the central angle of the developed cone could be found by multiplying 360 degrees of longitude by sine B sub O. Similarly, an angle on the grid between the central meridian and any other geodetic meridian can be found by multiplying their difference of longitude by sine B sub O. This angle is the plane convergence angle located at the apex of the cone. The plane convergence angle sometimes is called the mapping angle. Its symbol is the lowercase Greek letter gamma. We now can see that we have developed a giant right triangle, the conversion triangle. One leg of it is the mapping radius through the station. One angle of the triangle is the plane convergence through the station. Using classical Euclidean trigonometry, we can calculate the other two legs of the giant triangle. As noted on the screen, the leg along the northern axis of the grid can be found by multiplying the mapping radius through the station R by the cosine of the plane convergence angle. This yields the difference in northings between the apex of the cone and our station. Remember that we previously determined that adding N sub B with R sub B yielded the northing of the apex. Therefore, subtracting the value R cosine gamma yields the northing of the station. The northing is noted by the small letter n. Next, we see that the remaining leg of the giant conversion triangle, labeled R sine gamma, is shown. The value found by solving this trigonometric equation is positive if the station is east of the northing axis and negative if west. We can calculate the easting of our station, noted as small e, by adding the result to E sub O. Thus, we have a method to convert our station's geodetic coordinates, B and L, to its equivalent grid coordinates, small n and small e. Reversing the procedure provides for the inverse computation, starting with plane coordinates and going to geodetic coordinates. We will cover three broad classes of calculations for state plane coordinate systems in this presentation. They are, first, conversion